In this video, we're going to introduce a new magnitude called enthalpy, and we're going to see the applications of this new magnitude. First of all, enthalpy, this new magnitude, is the take-home message of this whole video is that enthalpy is pretty much related to internal energy. It's just a practical rearrangement of things. So instead of calling internal energy E, we will use H for enthalpy. But the concept should be very similar. How much energy does that system possess? First of all, let's get a little bit physical chemistry here, because this may help us understand why is it that we need to come up with a new magnitude when the internal energy was already pretty useful. So first of all, what we as chemists are interested is in measuring changes of internal energy. The first law of thermodynamics says that any change in internal energy is because the system has gained or lost energy in form of heat and work. For a gas expanding and contracting, or for the atmosphere for that matter, the work is negative pressure times increment of volume. We will not have much time to talk about this, but if you're taking physics later on or physical chemistry, you'll have a better understanding of why that is. What's important though is that, well, at constant volume, the change in internal energy is equal to the heat, right? Because delta V is 0, so good for us. And that's how we usually measure changes in internal energy. We just take the heat, but we need to make sure that delta V is 0. That's kind of impractical when, as chemists, we work at constant pressure. We want to come up with a magnitude that, when pressure is constant, the heat that we measure is somewhat related to the internal energy. So bear with me that we are going to come up with a new magnitude. We're going to do something called a Legendre transformation, and we take derivations here. There isn't much time to come up with it, but this will be the first law of thermodynamics, which should be equivalent to this one up here, written in terms of enthalpy. There is just this new definition, but conceptually, do not get lost by the mathematics of it. Conceptually is still the first law of thermodynamics. The good thing is that at constant pressure, and in our lab typically we work at constant pressure equal to 1 atmosphere, at constant pressure the heat that we measure is equal to the enthalpy. And this change in enthalpy, which is similar to the change in internal energy, will be what we can measure in a chemical reaction, for example. Okay, so now that we have introduced a little bit, and I apologize for all this very busy slide, is that instead of internal energy, let's call it enthalpy, but that's what we're going to use for chemistry most of the times. Okay, so how can we measure enthalpies? To do that, we are going to come up with a metaphor, if you will. Say that you're interested in studying the reaction when A becomes D. A is your reactants, D is your products. What is the change in internal energy, the change in enthalpy, which is similar to the internal energy? So how can we calculate that? If we know changes in internal energy from other reactions. So think of it as if you are someone up here taking the elevator, and this person first goes down 1 floor, then goes up 2 floors, and then goes down 4 floors. You could probably figure out the difference between A and D just by measuring how much ups and downs you have done in your elevator, which is the same as combining the reactions in here. Notice that if you combine the reaction in a way that B and B cancel out and C cancel out, A becomes whatever's left, which is D, and you just need to add D. What we were saying, right? Going down 1 floor, going up 2 floors, going down in here 4 floors. The overall is, I hope it's going to be going down 3 floors. In other words, this is positive, yep, this is going to be negative 30. What we just did here, to indirectly find the change in internal energy going from reactants to products through the combination of other reactants, this is called Hess law. And that's important because enthalpy, like internal energy, is a state function meaning it does not depend on the path. Enthalpy is the internal energy that a system possesses. So let's try to solve a practical chemistry problem applying Hess law. Imagine that you want to know the change in internal energy of this reaction. Why would we want to know that? Well, in this case, these are two relevant gases that that exist in cars. You may want to know how much energy would they need, how do they release any heat, etc. So say that you may know the internal energy, sorry, the change, I'll keep saying internal energy, but what I actually mean is enthalpy, but they're both related. I know the change in enthalpy for these two reactions. In what way can I combine these two reactions so that I can figure out the change in enthalpy? Alright, well, notice that I want CO2 on the right, CO on the left, so I'm going to combine equation A the way it is. And delta A is negative 2A3. Now B, notice that I want N2 on the right and NO on the left, and notice that I want just half of nitrogen. And so what I'm going to do is flip equation B and divide it by 2. So now instead of 2 I divide it by 2, so I have 1 NO, that becomes 1/2 of nitrogen and 1/2 of oxygen. And careful here, because if I flip the reaction and I divide it by 2, I need to do the same. So this new delta B is going to be negative B divided by 2, which is negative 180.6 kilojoules divided by 2. And when I combine these, what I get is the target reaction. So CO, no, this will disappear with this one, so I have, gives 1 CO2 plus nitrogen. And the change in internal energy will be the addition 283 minus 180.6 divided by 2. We applied the Hess law, in which we have combined different reactions to obtain our target enthalpy change.